Howdy! Today we will be solving problems on one-dimensional motion. One-dimensional motion. But before we start solving problems, we will write all formulas that we need for that. We will start with definitions. Definition of acceleration. Acceleration as a function of time is rate of change of velocity, dv dt. Velocity as a function of time is rate of change of position, dx of t dt. So since we restrict ourselves to one-dimensional motion, our goal will be to describe position of an object as time changes. I will call this formula 1. I will call this one formula 2. And now what I will do, I will take integral of both sides of equation 1. It will be integral a of t dt on the left. It will be integral, indefinite integral dv dt on the right. And all of you took calculus, so you know that antiderivative is just function itself. So the result of this integration is velocity as a function of time, and since this is indefinite integral, I need to add arbitrary constant. What I will do next, I will add one more formula for this list. 1, 2, now we will have formula 3, which will be also very useful. So if you are given acceleration, now we know that we can find velocity as integral a of t dt. This is indefinite integral. I did not rewrite this constant here because this is indefinite integral, and by taking it, I will generate another constant, which I use to satisfy the initial conditions. So it is 1, 2. We have third equation now. I will put 3 right here. Okay, what I'll do next, I will take indefinite integral of both sides of equation 2. Integral v of t dt on the left-hand side of the equation, and integral dx dt with respect to time. Again, antiderivative is function itself. It is x of t plus constant. So now, if velocity is given, I know how to find the position. Equation 4, I will rewrite it here. X as a function of time is integral v of t dt. Again, I do not rewrite this constant for the same reasons as I did when I rewrote equation 3. This is indefinite integral. It will generate arbitrary constant, which help me to satisfy initial conditions. That's it. That's all we need. Basically, we need formula 1 and 2, and we need to know calculus to have 3 and 4. What I'll do next? Next, I'll consider a very special case. I will consider case when acceleration is not function of time, and I will apply formulas 1, 2, 3, and 4 for this special case. Acceleration is constant. It does not depend on time. For example, you have a train that is moving with constant acceleration. Okay, this is a very practical situation, so we'll spend a minute talking about this. Since acceleration is constant, I go back to my equation 3. From 3, I have velocity as a function of time, which is integral a c dt. Since acceleration is constant and does not depend on time, I take it out of integral act, and that's indefinite integral, so it generates arbitrary constant. I need to know the initial condition to find these constants. So let's assume that the initial condition, which has to be given, is velocity at time moment 0 is v naught, where v naught is a given number. This is a number. That's not a function. This is a given number, initial condition. Now I will use this initial condition to find my constant. So what is velocity? This is velocity at any time moment. Now I will rewrite it at time moment 0. Time moment 0, so the first guy here is 0. Second one is constant, and according to our initial conditions, this constant is v naught. I'm ready to write velocity as a function of time for constant acceleration. Velocity as a function of time is ACT plus v naught. Constant is v naught. V naught. Okay, 1, 2, 3, 4. Let's call it 5. We are making progress. Okay, what's next? Next, I will use my formula 4 to derive position in this special case when acceleration is constant. From 4, I have x as a function of time is integral. I plug in the velocity. Velocity is ACT plus v naught for this special case when acceleration is constant, dt. Let's take this integral. We know what we are doing. AC is constant. I take it out of integral. Integral t dt will give me t squared over 2. I'm done with integration of the first guy. Second guy, remember, v naught is a number. It's constant. So again, I take it out of integral. Integral dt is just time. And we don't forget to generate arbitrary constant that we need to satisfy the initial conditions. So initial conditions have to be given. Let's assume that is the initial condition. I will not rewrite initial condition. I will just write x at time moment 0 is equal to x naught. Again, this has to be a given number. Now I'm moving right here to the left to continue. And I will have x as a function of time. Everything that is in red, pink, whatever you see, is for a constant, for acceleration constant. Okay, x as a function of time. I'm right here. AC, t is 0, so the first guy is 0. Oh, I'm sorry, I forgot to write that. I'm doing it at time moment 0. X at time moment 0 is this guy is 0, time is 0. Second guy, this guy is 0, time is 0. I'm left with constant. And at the same time, from my initial condition, I know that x at time moment 0 has to be equal to x naught. So what is the final formula? X as a function of time is, I put here c to emphasize that this could be used just for the case when acceleration does not depend on time, plus v naught t and plus x naught. Oh, look at this. Now we have formula 6. So this is 6. And if you are creating a formula list for yourself while you are listening for me, so please write 1, 2, those are definitions. 3, 4, you can write them. They follow from 1 and 2, but still having them in front of you could be helpful when you start solving problem and figuring out which formula to use. And then for this very special case, when acceleration is constant, you have formulas 5 and 6. Now I will keep my red acceleration constant, and I will derive one more formula that also could be useful. So this formula will exclude time. If time is not part of your problem and you're looking just for velocity or position, you can exclude time from formulas 5 and 6 and have a formula that has only velocity and position. Let's do that. So the easiest way for me to derive it is to use definitions 1 and 2. Just keep in mind the acceleration is constant. So AC is dv dt. That's the first equation that I will use. And the second equation is v is dx dt. So I will take equation that is marked as star and will divide it by equation that is marked by 2 stars. I will have AC over V on the left, and I will have dV over dx on the right. What I will do next I will multiply by dx and multiply by V both sides of equations, which means that I will have AC dx on the left, and I will have V dV on the right. For a change, I will take definite integral of both sides. I will assume that at time moment t1, the object was at the position x1. At a time moment t2, and velocity at time moment t1 was v1. At time moment t1, position was x1 and velocity was v1. At time moment t2, the position of the object was x2 and the velocity of the object was v2. Now I take this integral. What will we have? Remember, AC is constant, so what I have on the left is AC and then x2 minus x1. What do I have on the right? On the right, I have v squared over 2 as the result of the integration. V squared over 2. The limits are from v1, this is v, v1 to v2. And if I plug in the limits, what will we get? We will get v2 squared minus v1 squared over 2. Now, I will add this last formula to our list. What is this formula that you have to add to your list? It is, let me do this. I will steal some space here. I will do it like that. And then I'll have enough space, hopefully. So, I have 2 will come to the left, and I will start with writing v2 squared. v2 squared minus v1 squared. This is my one side of the equation. 2 comes to another side of the equation. So it is equal to twice AC x2 minus x1. This is formula number 7 that you can add to your list of formulas. Be careful when you apply anything that is in pink. Formulas 5, 6, and 7 can be applied only in the case when acceleration does not depend on time. Formulas 1 and 2 always work, and formulas 3 and 4 follow from definitions 1 and 2. Now we are ready to solve problem 1.